A hash function is like a magic fingerprint machine for data. It converts data into a unique fixed size fingerprint. Data goes through a hash function, usually an MD5 or an SHA-256, and it spits out a hash, also known as a digest. This input can be of any arbitrary size. It could be a single word or it could be a long string of text, but the resulting hash is always a fixed size random string. These hash functions are deterministic. They'll always give you the same output for a given input. They are also computationally efficient. It only takes a few milliseconds to convert a string of text into a hash. The output size is fixed. No matter the size of the input file, you'll always get a fixed length hash as the output. These hash functions are also one way. They cannot be reversed. You cannot derive the input from a given hash. A small change in the input leads to a big change in the output hash. Here you can see that I have just changed one punctuation mark and the entire hash has changed. And it's very hard to find two different inputs that will lead to the same hash when put through a hash function. Hash functions are used widely in the modern day digital systems. They are used to store passwords. The passwords are hashed and then stored in the system so that even if the system gets compromised, the passwords don't get leaked. They are also used to check the integrity of a file. They are used in Git and version control. Every commit that you see is a hash, and the entire code history is basically a chain of hashes. They are also used in search and databases in the form of hash tables because they enable faster lookups. And they are also used in digital signatures to verify the identity and integrity of someone's signature. We need hash functions because they enable trust, efficiency, and security at scale. Any kind of open network like internet or blockchain where there are multiple anonymous participants operating independently across the globe need some way to trust each other when it comes to data communication and coordinating with each other. That's why the general applications of hash functions include representing data by creating a deterministic ID of a data so that you can communicate the ID over a network and refer to a piece of data. You can compress any kind of data and compare the final output for efficient comparison. A 100 MB file or a 100 GB file would result in a very small hash, and you can compare the hashes instead of comparing the original file to check if they are the same or not. You can also verify data integrity. You can compare the hashes of a file while transmitting it over a network to check if the file has been tampered or not. If the file has been tampered or altered in any way, the hash would change. And lastly, they are used for data privacy. Wherever you need to store some sensitive data or you need to prove that you know something without actually revealing the data, a hash of the actual data is stored in the system instead of storing the actual data so that if the system is compromised, the data still remains secure. Hash functions are not encryption. You cannot decrypt the output back into the input. Hash collisions are still theoretically possible because ultimately there's a finite space of possible output hashes. Weaker hashes can compromise your system security. Like earlier, people used to use hash functions like MD5, etc. As the computing power of the industry increased in general, these hash functions became weaker and the industry moved on to better and more secure hash functions. This is still a lying threat with quantum computing. If quantum computing becomes mainstream, the present hash functions would become ineffective and we might need to move to quantum resistant hash functions. Hash functions are also not authentication. They cannot prove whether somebody sent some data or not. They simply represent the data. Hash functions are one of the fundamental building blocks of Web3. Web3 is built on blockchains, and blockchains are built on three main cryptographic primitives, which are hash functions, asymmetric cryptography, and digital signatures. So they are widely used in blockchains for representing data, for referencing it, and for verifying it. Some of the commonly used hash functions in blockchains are SHA-256 and KECHAC-256. They are used in creating account addresses. A general account address or a NEO address is a hash of the public key, whereas a contract address is the hash of the creator's account address plus some random value. They are also used in Merkle trees. These trees are used to store transaction data, blockchain state, etc. Basically, each leaf node of this tree is a hash of some data point, and from then there on, at each level, the node of the tree is a hash of its child hashes. This goes on up until the root of the tree, which is often called as the Merkle root. Hashes are also used in creating a block hash. Block hash is a unique identifier representing each block, and it is derived by putting the entire block data through a hash function. This data often includes the transaction data of the block, the address of the node who proposed the block, the previous block hash, timestamp, etc. Lastly, they are also used in content addressing in IPFS. IPFS is the interplanetary file system, and it's like a distributed file system for the internet. Hashes are used to create CID or content ID, which is used to locate and retrieve data in this file system. Because of the way block hashes and Merkle trees work, blockchains heavily rely on nested hashing. This makes blockchains tamper proof. If you change any single transaction, every hash leading up to the root of the Merkle tree also changes, and this Merkle tree root is also a part of the block data along with the hash of the previous block. So the hash of that block also changes, and because of that, the hash of the next block will also change because it depends on the current block hash. This is why on blockchains, if you change any one single thing in the past, everything in the present needs to change as well. Not only that, each node running and maintaining the blockchain also needs to agree on these new changes again. So in short, hash functions together with the decentralized nature of how blockchain is run and maintained gives blockchain its another key property, that is immutability. Now before I go, the hashes in all of the examples given in this video were generated using this generator. I'll leave a link to it in the description below. Feel free to redo the examples and verify them yourselves. Thanks for watching. You can ask anything in the comments or suggest a topic that you'd like to know more about. Subscribe more for such videos and like and share so that these videos reach more and more relevant people. Also remember that nothing in this video is a financial advice. You have to do your own research.